Where do tornadoes and tropical storms come from? Tornadoes and tropical storms stem from eye-shaped columns of hotter air, surrounded by colder air. These columns of hotter air are nurtured by hotter grounds in the case of tornadoes, or by hotter ocean zones in the case of tropical storms, which are found right below the eye-shaped columns. These hotter grounds and hotter ocean zones act as fuel tanks that supply tornadoes and tropical storms with energy, and maintain them until the eye-shaped columns cool down. Without these fuel tanks, eye-shaped columns of hotter air cannot develop, and therefore, tornadoes and tropical storms cannot develop, too. These eye-shaped columns of hotter air are similar to eye-shaped columns of hotter air right above big fires, and these big fires nurture the eye-shaped columns of hotter air right above them until they are extinguished. So, what happens next after the eye-shaped columns of hotter air have developed? Because the air inside these eye-shaped columns is hotter, it expands and becomes lighter than the air outside the columns, which is colder air. The buoyance force exerting on the hotter air therefore outweighs the gravitational force exerting on it. So the air is driven upward. When the hotter air moves upward to the higher layers of the atmosphere, it leaves a low-pressure zone at the bottom of the eye-shaped columns, and this low-pressure zone is usually called depression, or tropical depression, or just a low-pressure zone. On the contrary, on the far side from the eye-shaped columns, air is colder. It therefore contracts and becomes heavier. The gravitational force exerting on the colder air outweighs the buoyance force. The air is therefore driven downward, to the lower layers of the atmosphere. This colder air also creates a high-pressure zone near the ground, or sea surface, far from the bottom of the eye-shaped columns. The difference of pressure between the bottom of the eye-shaped column and its surroundings drives inward flows of air, toward the bottom of the eye-shaped columns. On the contrary, at the top of the eye-shaped columns, the difference of pressure between the top of the eye-shaped columns and the surroundings drives outward flows of air. All these flows of air constitute a closed circulation of air in the similar way to two interlocking cogwheels. However, the inward flows of air are not exactly what tornadoes and tropical storms look like. Tornadoes and tropical storms are strong winds moving in something like circles. They are not just inward flows of air. So, how are these inward flows of air transformed into circles in reality? The answer to the question comes down to the rotation of the Earth around its own axis, or more exactly, the Coriolis effect produced by the rotation of the Earth. The whole transformation mechanism is summarized as follows. The distance, d, from a point on the Earth's surface to the Earth's rotational axis varies with the latitude at which it is. So, if a motion of an object on the Earth's surface involves in the variation in the latitude, the distance from the object to the Earth's rotational axis also varies. Because of the momentum conservation law, the variation of this distance, in turn, leads to the variation of the angular velocity of the object around the Earth's rotational axis. This variation finally turns the inward flows of air into something like circles, which are tornadoes or tropical storms, depending the location where they are. The following is a set of 3 examples illustrating how the variation in latitude leads to the variation of the distance d. If the latitude is 30 degrees north, the distance d is r times cosine of 30 degrees, which is equal to square root of 3/2 times r, where r is the radius of the Earth. If the latitude is 45 degrees north, the distance d is r times cosine of 45 degrees, which is equal to square root of 2/2 times r, which is shorter than that of the latitude of 30 degrees north. If the latitude is 60 degrees north, the distance d is r times cosine of 60 degrees, or 1/2 of r, which is shorter than that of the latitude of 45 degrees north. So, in the northern hemisphere, the higher the latitude is, the shorter the distance from the location to the Earth's rotational axis is. Now, take a look at another example illustrating how inward flows of air is transformed into a tropical storm by the rotation of the Earth. The hotter ocean zone is a circle in the Atlantic to the east of Florida. The center point of the hotter ocean zone, point O, is at the longitude of -70 degrees west, its northernmost, point A, is at the latitude of 30 degrees north and its southernmost, point B, is at the latitude of 25 degrees north. If the Earth did not rotate around its own axis, there would be only inward flows of air from the periphery of the hotter ocean zone to its center. However, when the rotation of the Earth is taken into account, the inward flows of air are transformed into cyclones because of the variation in the distance from the flows of air to the Earth's rotational axis. The following are two examples illustrating the transformation of the motion. If a mass of air flows from point A, the northernmost of the hotter ocean zone, to point O, the center of the hotter ocean zone, it moves from the latitude of 30 degrees north to the latitude of 27.5 degrees north. So, the distance from the mass of air to the Earth's rotational axis increases by an amount of r times cosine of 27.5 degrees minus cosine of 30 degrees, where r is the Earth's radius. The angular speed of the mass of air around the Earth's rotational axis reduces, the flow of the air is therefore shifted to the west of the line segment AO. On the contrary, if a mass of air flows from point B, the southernmost of the hotter ocean zone, to point O, the distance from the mass of air to the Earth's rotational axis reduces. So, the angular speed of the mass of air around the Earth's rotational axis increases, the flow of air is therefore shifted to the east of line segment BO. In conclusion, all inward flows of air in the north of the hotter ocean zone, or above the point O, are shifted to the west of their radii, because their angular velocities around the Earth's rotational axis reduce during the transition. Similarly, all inward flows of air in the south of the hotter ocean zone, or below the point O, are shifted to the east, because their angular velocities around the Earth's rotational axis increase during the transition. So, the tropical storm to the east of Florida has been created from the existence of the hotter ocean zone. The important thing to be noted is that this tropical storm, a tropical storm in the northern hemisphere, rotates counterclockwise. All tropical storms and tornadoes in the northern hemisphere rotate counterclockwise if they are observed on a map. The reverse is also true. All tropical storms and tornadoes in the southern hemisphere rotate clockwise if they are observed on a map. Regardless of the name, tropical storms and tornadoes never occur right on the equator, because in this case, northern hemisphere air tends to rotate counterclockwise, but southern hemisphere air tends to rotate clockwise, which is opposite to the northern hemisphere air. So, people who live in countries like Ecuador will never see any tornado nor tropical storm. The height of a tropical storm can be up to 10 kilometers, or 6.2 miles. Meanwhile, the height of a tornado is about 1.5 kilometers, or about 1 mile, which is much shorter than that of the tropical storm. The difference in the height is because the amount of heat energy supplied to tornadoes by the hotter ground is much less than that supplied to tropical storms by hotter ocean zones. Heat capacity of water is around 4,200 joule per kilogram Kelvin. Meanwhile, heat capacity of soil and rock is less than 1,000 joule per kilogram Kelvin, which is less than 1/4 of that of water. So, of the same temperature, the amount of heat energy that an amount of water contains is about 4-fold higher than the amount of heat energy contained in the same amount of soil and rock. In addition to this, seawater also facilitates the convection of heat. If ocean surface cools down for some reasons, cold water on the ocean surface will sink to the seabed, and hot water near seabed will rise to the ocean surface, replace the cold water, and maintain the high temperature of ocean surface water. This form of circulation continues until the temperature of sea surface is equal to or higher than that of seabed. In other words, source of heat energy supplied to a tornado is limited, but source of heat energy supplied to a tropical storm is much more available. Because of these differences, a tropical storms can last for more than a week, but a tornado usually lasts for just 1 or 2 hours. Tornadoes and tropical storms can be likened to heat engines. A heat engine, for example, a steam engine, needs both a hot source and a cold source. On the way heat energy is transferred from the hot source to the cold source, it produces work. Similarly, hot sources of tornadoes and tropical storms are either hotter ground or hotter ocean zones. Cold source of tornadoes and tropical storms is the upper layers of the atmosphere. On the way the heat energy is transferred from lower layers to the upper layers of the atmosphere, they produce work in the similar way to steam engines do. The higher the difference in temperature between the lower layers and the upper layers of the atmosphere, the more violent the tornado or the tropical storm will be. The development of the hotter ocean zones can come down to ocean currents. Ocean currents can be likened to supergiant vessels that carry heat energy from ocean zones to ocean zones. These ocean currents can bring to an ocean zone a massive amount of heat energy and transform that ocean zone into a hotter one, which in turn facilitates the development of tropical storms. Meanwhile, the hotter ground that develops into a tornado is usually caused by the difference in heat capacity of the materials that make up the ground. For example, ground with a lot of trees is colder than ground made of only sand and without trees. If a vast area is made of sand only, and the surroundings are covered with trees, it is highly likely that the area of sand become the hotter ground and it may trigger the development of a tornado there.